In our first lecture on heat conduction, we looked at the theory that was general, but most of our applications were one-dimensional. In other words, line elements for heat conduction. Now we'd like to get into 2 dimensions. Also, I'd like to review the variables that are involved and show some of the mappings between the various heat conduction vectors. We'll end up with a small problem session. Let's discuss the variables involved in heat conduction. You may have done classical heat conduction before, and often flux is considered a vector-like quantity. We're going to concentrate our attention on what happens at nodes, and so for us, flux is more often a scalar, and it's positive into a point and negative out of the point. We can make also equivalent nodal fluxes that come from volumetric or surface flux by integrating over that relevant domain. Let's review the structural notation that we've used earlier in this course. We had the nodal quantities, the u displacement and the F force, and their product was work. We had strain and stress, and their product was work per volume. It was strain energy density. We had the distributed forces in 1, 2, and 3 dimensions that when multiplied times the field displacement gives the work for whatever spatial dimensions that is. Now, we didn't work so much with the generalized coordinates multiplied by generalized forces over here. It was the generalized forces that we really didn't exploit. Those are such as Argyrus's natural modes. They're methods that aren't used so much anymore, so I haven't concentrated on that. But the interesting thing is that you can identify energies here, or work done, by looking at a quantity in blue multiplied by a quantity in red. So you have a displacement-like thing and a force-like thing. Also, we had equivalent nodal loads that were made by doing the proper spatial integral of the distributed force. Now, these concepts aren't quite as obvious in heat conduction, but there are similar situations. For heat conduction, we can also form work by multiplying the relevant quantities. On the right we have the temperatures, and on the left we have the fluxes. Here we have the nodal temperatures, and over to the left the nodal fluxes, so their product is work. Then we have distributed fluxes, both volumetric and surface, and then we have the field temperature, and their product is the work per space or per dimension over which the integration is to be taken. And that integration is shown here to convert from a distributed flux into a equivalent nodal flux. We need to do this integral multiplying the distributed quantity times the field displacement as characterized by the shape function. Let's review the dimensions and units that are used in thermal problems. Temperature doesn't have a universal symbol. I might suggest a theta here, which is often seen. But it can be in English, in Rankine or Fahrenheit, or in metric in Kelvin or Celsius degrees. The remaining quantities are similar as to the mechanical problems, using the conventional dimensions, length, time, energy, and power, and then having that either in the English or in the metric units here. Of course, metric is winning big worldwide, and many Americans are coming over to metric now, and you'll notice that I'm using it more and more in my notes. When I was in graduate school at the master's level at Iowa State, there was quite an emphasis on similitude, which was the idea of finding analogies in different fields. And so we often found ourselves using an electrical network to represent a fluid system and a mechanical system to represent electrical and so on. And there is quite a comparison between this thermal and the mechanical problem area. For instance, I'm going to compare structural mechanics and heat transfer. And if you take this analogy, you'll take the displacement and the temperature as corresponding, then velocity, and in heat transfer, the rate of change of temperature is a time change of temperature. The acceleration that is in structural mechanics really has no equivalent over in the thermal problem because the second derivatives are not important. Stiffness would play the role of thermal conductance in heat transfer. Damping is played by heat capacity. There is no mass analogy in the thermal problem in the way we're making the analog. And the applied load is indeed a thermal load. And you will see the term thermal load used quite a bit in the finite element codes. My goal in this lecture is to progress from one-dimensional heat conduction into two-dimensional. We're not going to do much with three-dimensional, but I think the progression is clear. Now, in two dimensions, one of the easiest elements is the triangle, and it helps if we start with a simple triangle, namely the right triangle. I regard this as a special case because of the simplicity of the triangle itself. What I'm going to do is calculate one of the relevant heat conduction coefficients, K33, and show equivalent fluxes for the distributed flux shown that's on the edge of the element. The element has thickness h. In our previous lecture, we developed the three-dimensional law for the heat conduction coefficients. Now we'll specialize it to two dimensions. And here we have an integral over the volume of the body, but that's represented by the thickness of the material times its area. We don't need the derivatives in the z direction, but we do have these x and y derivatives. The shape functions occur naturally in the ij pairs in the same way as the coefficient has its indices. You can see that the whole stiffness depends upon the shape functions, and those in this case are going to be plane surfaces in the same way that the Turner triangle was developed. I've sketched one of them here, namely N3, which is one of the simpler ones because it has a unit elevation over node 3, and that is quite easily found to be y over c, where c is the y coordinate out at node 3. Then the other two are also found in like manner. The first shape function, of course, depends on the equation of the line here. We'll calculate the term K33, and it depends on the third shape function only. It has the derivatives both on x and y shown here. Now, N3, quite simply, was the quantity y over c, and so when you take a derivative on x, these terms drop out and give us 0. The derivatives on y give you 1 over c squared. This is a constant, and you shouldn't be surprised because this is a constant gradient triangle. You end up integrating the area with these constants out front. The area becomes ultimately the base times the height divided by 2, and then upon simplifying you get the expression for K33, KHB over 2C. Now we could continue this for the other coefficients in the matrix, but I'll show those in general for the general triangle a little later. Let's calculate the equivalent nodal flux due to the distributed flux on the left boundary of the element. The general integral over a surface involves the flux and then the surface area in this case. Our surface area is the thickness of the material times the differential height. The flux at that surface is constant Q0, and then we have to evaluate the shape functions on that left boundary. This is actually an integral on that line where the load is applied. Then when we carry that out, we'll put in the coordinates on the line, 0 and y for x and y. That leaves the first shape function in the form 1 minus y over c. The second shape function is identically 0 along that line. The third shape function is y over c. We carry out the integration term by term in that vector. It involves values of y, and then those integrate into y squared. The second component is 0, and then we find these equivalent nodal fluxes. Now the components themselves are just scalars that are positive into the nodes in question. The fact that there's no equivalent nodal flux into the remote node over here has to do with the fact that the second shape function is 0 along this boundary. As a result, that boundary flux can do no work on that particular shape function, and therefore we have no equivalent nodal flux due to it at node 2. After doing that right triangle, I decided, gee, we really need the general case, just as we did in structures. So I set up this triangle with a certain special or element coordinate system centered below the vertex. And now I allow for a coordinate minus a at this left node and plus b at the right node, giving a base of a plus b, and then a coordinate of c for the y-coordinate at the upper vertex, so the altitude is c. And after turning the crank quite a few times, you end up with this matrix for heat conduction, and that's general then for any triangular constant gradient heat conduction triangle. Our first problem is one where we take a right triangle heat conduction element and put a known flux in at one node and then ask what the temperature results at that node. This is a 3-noded constant gradient triangle. We put 100 watts in at the top node, holding the bottom 2 nodes at 0 degrees Celsius. And what temperature does the node number 3 reach after a long time? Now this means we're looking at a static problem, so it's a steady state problem. I give some physical values for the material of this triangle. It's a 1 millimeter thick triangle. You can see the dimension here of the altitude and the base of the triangle. Here's an expansion coefficient, and here's a heat conduction coefficient. I found over the years when you put in extraneous information such as the expansion coefficient that students really can panic, and I think professors need to do more of that. I really feel that we don't let our students get the exposure to real-world problems enough. Where there's extraneous information, there's lack of information, and so that was an attempt to add irrelevant information. Now we had found that coefficient K33 for the right triangle, so we're in good shape. We can write out the heat conduction matrix. We've held the first 2 nodes to be 0 and allowed the third one to take some unknown value. And then we've imposed over on the right the 100 watts of flux. So solving this is a straightforward problem with this coefficient times this unknown to be equal to this known. And you just solve for U3, putting in the proper terms, the heat conduction coefficient and the dimensions, and you end up with 20 degrees Celsius. In the body of this lecture, I gave the heat conduction matrix for the general isotropic triangle. Now I'd like to go through a calculation, though, just to show how that would be done in detail. We'll only do one term, but you'll see that it's quite intricate. I've posed this problem in sort of an inverse way by asking the following question, that if you have this triangle and it's an isotropic material, constant thickness H, and if you raise the temperature at node 1 by 1 unit in temperature and then hold nodes 2 and 3 at 0 temperature, what is the heat flux into node 2 that's required to maintain this situation? Now, in effect, what I'm really asking for is the term K21, because that's the heat that's required at node 2 to maintain a 1 unit temperature rise at node 1. We have the general expression for the heat conduction matrix, so we can find K21 rather quickly. Here is the expression, and we need to be able to take derivatives on n2 and n1 by both x and y. First, though, we need to figure out the shape functions, and those are a little tougher now in this general triangle. First of all, n1 would have to raise this node over here 1 unit, and would have to pass through 0 on the far side, making use of that equation. So I do that here in the product form. You then evaluate that at the left node and set it to be unity, and thereby letting you calculate what the magnification factor, capital C, is. And here's the scale factor that we find. So that gives us our first shape function. Now we need to take derivatives of that function with respect to both x and y, and I show those derivatives here, and then try to simplify them a bit. So these are 2 of the 4 ingredients needed in the integration. The second shape function is found in a similar way using the product form. Again, we leave a scale factor and then the equation of the relevant line. We evaluate the shape function at its home node where it has unit value, put in the coordinates of the second node, solve for the constant, and then reinsert that into the shape function expression. Then we need the 2 derivatives, both on x and y, and those are done here, and then slightly simplified. We now have all the terms in the integral. So here we can find our coefficient K21, having calculated these 4 needed quantities. In fact, those are all constants, and so that the integral over the volume becomes that integrand, and the thickness of the triangle and the area of the triangle are the volume contribution. We put the terms in, simplify, put them over a common denominator ultimately at the bottom, and that gives us our coefficient K21. This is only one of the heat conduction coefficients, and there are some 6 independent coefficients in the symmetric 3×3 matrix, but the others are carried out in a similar manner and then yield the matrix that we showed earlier in the lecture. So that finishes our discussions on heat conduction.